Hey y'all, in this lesson, you're going to be learning about the T-interval procedure, which is the way you find a confidence interval when the population standard deviation is unknown. We've talked a lot about z-scores and z-interval procedures and lots of things when the population standard deviation is known. And we've looked a lot at the standard normal curve and standardizing variables and all that good stuff. Well, oftentimes, especially in the real world, the population standard deviation is unknown. And in this case, we want to use what's called the student's T distribution. And this was discovered by a person named William Gossett, and he worked for Guinness Brewery. He did some work that he wanted to publish anonymously. Actually, I think the company made him publish it anonymously. And so he published it as student. And it is the student's T distribution because of that. So that's kind of a famous story. Just a review of some of the other stuff that we've looked at that's leading into this. You can see some of the overlap and the similarities here. We started with just a z-score and the formula for a z-score. Remember, a z-score is the number of standard deviations something is from the mean. So this was the formula we used when we had the population mean and the population standard deviation, and then one of the values in the data set. And then we moved on to the sampling distribution of the sample mean. And for that, we had a different z-score. We still know the population standard deviation, but it's based on a sampling distribution, and we had to adjust for that by taking the square root of n and dividing it. Which leads to our last one, a t-score, and it's the same formula. The only thing that's different is that we don't have that population standard deviation. So instead of that, we're going to be using a sample standard deviation. And this is going to change some of the characteristics of our curve. We're no longer going to be dealing with a standard normal curve, and instead we'll be dealing with a T curve or a T distribution. A normal distribution is identified by its mean and standard deviation. A T distribution is identified by what's called degrees of freedom, or DF. And this is found by doing n minus 1, so sample size minus 1. And this is just saying it's the amount of variation we can expect from a data set. So for example, if we have, if you're taking 4 quizzes in a semester, and on the first 3 quizzes you made an 80, then I could probably expect you to make around an 80 on the 4th one. So it's just that amount of freedom that we have when we're predicting behavior. And then T distributions are still mound-shaped, kind of bell-shaped like a normal curve, but they are more spread out. And when I was learning this as a student, I wonder, why is it more spread out? I can't just accept that as truth. I have to know why. So in anything in statistics or mathematics, really, you should always question why and dive right into that. So what happens here is for a sampling distribution, for example, it's only varying based on sample mean because we know the population standard deviation. With a T distribution, not only are things varying based on sample means, but now they're also varying based on sample standard deviation. So 2 things are varying. It causes it to be a little more spread out. And so the shape takes on a little bit different characteristics. But I will say that as sample size gets larger, your shape will actually take on more of a normal curve. And if you look at a T table in your book or online, and you look down at the bottom of the T table and you compare those values with a Z table, you're going to find that they're the same. So the larger your sample size gets, the closer to a normal curve characteristics you're going to have. And this is just kind of showing that here. This first curve is a little more spread out, and then it tightens up, and then it gets even tighter. And you can see that that's because the sample sizes are getting larger, or degrees of freedom. So We want to find a confidence interval for a population mean when the population standard deviation is unknown, and that matters. Remember that when you do know the population standard deviation, you use a Z interval and Z scores. When it is unknown, you use a T interval and T scores. We still have conditions. As with anything, we have conditions that have to be met before we can use this procedure. And these conditions are the same as a Z interval. The sample must be randomly selected. The sample size must be large. If it is not large, the population needs to be normally distributed. Keep in mind that the sample size can be small if the population is normally distributed. It has to be one or the other. And this is kind of a review, so I'm kind of going quickly through it. If the sample size is small and you're not sure about how the population is distributed, then you can proceed, but should be very cautious about making inferences regarding the population. And then the third condition is that the population standard deviation is unknown. To calculate the confidence interval, we have to look at a t-table for finding the critical t-value or t-score. Remember that for alpha, we do 1 minus the confidence level, and then it was a two-tailed type thing, so we actually ended up using alpha over 2. I'm speeding through that because this was all part of the Z interval procedure, so there's all overlap here. If you'll remember, we sketched a curve, and we shaded that curve. I can show you real quick. That's really ugly, but you get the drift. We shade in here. We could say, this is the confidence level, and then that leaves alpha, which is split into 2 pieces, and that's why it's alpha over 2. So if we had a confidence level of 90%, that leaves 10% to be broken up into 2 pieces, which is 5% each, which is 0.05. So that's how you set that up in case you missed that or you forgot. And then you have to know your sample size, your degrees of freedom. So if we were to look at this t-table with a 90% confidence level, then our percent would be, or our alpha over 2 would be 0.05. And then let's say we had a degrees of freedom of 10. Then you just follow your fingers down 0.05 and 10, and then there's your critical t-value. So very simple. So in this next example, I want you to practice on your own, come back and check your answer. It is a 95% confidence level with a sample size of 25. So here's the table in case you need to see that, and go ahead and try it. Come back and check your answer. I showed my work here so you can kind of see where this is coming from. We have a confidence level of 95%, which leaves 5% left over for the 2 tails. So we split that up into 2, and that's 2.5% or 0.025. And I drew a little picture of that so you can kind of see what's happening there. And then what we're looking for are these 2 critical t values that represent t sub alpha over 2. And in order to find that, we need the degrees of freedom based on the sample size. So we go up to our table, we locate 0.025, we locate 24, and we get a critical t value of 2.064. And then that would be negative over here, positive over here. And that's it. That's all you're looking for, which is going to help us do confidence intervals. So that'll come into play in a second. You can also use your calculator to do this. You go second vars and then look for inverse t. We have been using inverse norm because we've been using the normal curve, but now we're using the t curve, so you'll use inverse t instead. And then also don't forget, if you're using your calculator, you do have to input those degrees of freedom. So I want you to pause it, check your calculator, come back and see. So I went to second vars inverse t, put in that alpha over 2 degrees of freedom, close it, and you can see I got that negative 2.064 if we round, which gives us that left piece. And the reason why it gave us the negative side was because remember your calculator assumes to the left. So if you wanted the right one, the positive one, you would have to account for this entire piece here to get that t value, which is fine. You can do that, but just know it's symmetric. So if you get the negative one, you have the symmetric one. And then here is the formula to find the confidence interval for a t interval. So that piece before was important because we need that critical t-score in order to finish out our interval or confidence interval. So for the confidence interval, it's almost exactly the same. It is the same process, different pieces as the z interval. We still need that sample mean. We still need that confidence level and critical t value. Now we need the sample standard deviation, and then we still need that sample size. So similar information as the z interval, just slightly different based on different information. So just to kind of go back over that, x bar is the sample mean, s is the sample standard deviation, n is the number of samples. I think that's actually sample size. Anyway, sample size. Here we go. So let's put together a confidence interval for 95% confidence when n equals 36. And that's going to help us find our t-score. So I want you to pause this, try to finish this problem, come back and check your answer. For the first part, you might have accidentally used the t value from the previous example that I showed you, but this is different because the sample size is different. So the sample size is going to kind of change the tightness of that curve, which is going to change where that t value is. So for our degrees of freedom, you're going to want to input 35, which is based on a sample size of 36. And we still are going to use that 95% confidence, so it's still going to be 0.025 for that area that we're looking for. And you should end up with a t-score of 2.03 or negative 2.03 for both sides. And then if we were to build a confidence interval, it's still going to be that same process. We still need the sample mean. We still need plus or minus the t-score times standard deviation over square root n. And then we'll simplify that. 3 over 6 is 0.5. And then calculate what that is. If you were to type those two pieces in separately, because remember from the previous lesson, the plus or minus represents two different values, and they represent those boundary points of your interval, your confidence interval. And remember that your mean, which is a measure of center, represents the center of your interval. So you're going to have to type in both cases, the 20 minus 2.03 times 0.5, and then 20 plus 2.03 times 0.5. And you should end up with this interval. And then to interpret that, all you have to say is something like, we can be 95% positive, or I'm sorry, 95% confident that the population mean lies between 18.985 and 21.015. And that's all it's asking for. Then in this last question, it says, what was the margin of error in this confidence interval? So if you know the center and you know the endpoints, then with that information, you can find that buffer. We talked about a buffer when we did the Z interval. So the buffer is that space in between. And if you're having trouble envisioning that, you can always draw a picture. So if I drew a picture of a number line, and we know that 20 is the center because it's the sample mean, and then we know our boundaries, 21.015 and 18.985, then this space, this buffer, is our margin of error. And that is 1.015, which comes from this piece right here. So you can see it two different ways. You can see it from when you form your or fill in your formula, or you can see it from knowing the distance between the center and the edge. And then as always, you can do all of this in your calculator. It's very fast. And as long as you type it in correctly, it leaves less room for mistakes. So, if you calculated something wrong or did something wrong in your head or whatever, the calculator just kind of eliminates that. So I have a couple examples down here, but here's the instructions to get there. It's the same as the Z interval, it's just you press T interval instead. So you're going to go to your calculator. You're going to go to Stat, go over to Tests, and we want a T interval. And then you're just going to input your information. If you have, instead of stats, if you have a data set, you can select data and you can input that data and you'll get the same stuff. But in this, we have statistics. Remember, statistics are just numbers. So we have some numbers that were given to us. Statistics are numbers based on a sample. Remember, parameters are numbers based on a population. So we have statistics, and we're just going to input that. We've got 20 for our sample mean. Our sample standard deviation is 3. Our sample size is 36. Our confidence level is 95. Hit enter. And that checks out with the one we just did by hand. So we know that the one we did by hand matches the calculator. We're good to go. So I want you to use your calculator and fill out the rest of this table. If you would prefer to do it by hand or even both ways to get extra practice, that's a great idea, a great way to study. But in either case, I'm happy as long as you're understanding what you're doing. So go ahead and try the table, come back and check it. All right, so you may want to check your confidence intervals. And one thing that you want to check, not only with mine, but when you're doing this on your own, is make sure that your sample mean is within your confidence interval. If your sample mean doesn't even live inside your confidence interval, then you've done something wrong. And I did this, so I just wanted to make sure and point that out just in case you've done the same thing. Just be extra cautious about what you're typing in, that you're typing in all the right numbers, make sure you double check it. And then when you get your interval, if that interval doesn't even make sense, then you might go back and just make sure. So these are the numbers. Second time, I did this twice. So second time around, I've checked it 3 times. Hopefully we're good now. Hopefully I fixed all the mistakes. But those are your intervals, and then all the interpretations are pretty much the same. You're just going to change the percentages and your boundaries. So let's draw some conclusions here. I want you to notice some specific things about there's a gnat and this patterns, I guess. So how did changing the mean, only the mean, affect the interval? Let's look at these first two here, where only the mean was changed. If you notice, the mean changed by 5. How much did the interval change by? Also 5. So it just shifted our center over. Shifts the center and boundaries. by however much the center changed. So the center changed by 5, which made the boundaries change by 5. How did changing the standard deviation affect the interval? So let's find one where only the standard deviation was changed. Let's see which one qualifies. There's a 3, there's a 9. Right here, same confidence, same sample size, same mean. So we're going to be comparing these two. How were they different? So when the standard deviation was larger, what happened to the confidence interval? If you think about it in terms of a number line, in the first one, we're starting at 18 and ending at 21. I'm rounding, terrible rounding, but just kind of lopping it off. 18 and 21 is now 16 to 23. So a larger standard deviation resulted in a wider net. As S got bigger, our confidence interval also got bigger, which means larger standard deviation, wider interval. Having trouble writing. There we go. And then how did changing the sample size affect the interval? So let's find one where only the sample size changes. Whoops, wrong tool. There we go. Sample size, let's see, here's one and this one. So compare those, draw your conclusions and come back. If we compare these two, when n is larger, what happens to our confidence interval? So we went from 18 to 21 to now 19 to 20. So it's shrinking in. So as n gets bigger, as sample size gets bigger, our confidence interval gets smaller, which means that we're narrowing in on estimating that population mean. So the more samples we gather, the closer we are to narrowing in on getting that true number. Last one, how did changing the confidence level? So only the confidence level changes. I believe we can look at these last two here and compare those. How do these compare? Pause it, try it, come back. So when the confidence level got bigger, when we say 99% confidence, if you look at the numbers, it's close, but the confidence interval got slightly wider, just a little bit, not much. 0.4, about, I'm estimating there, about 0.4. So when we have a larger confidence level, we have a wider confidence interval, because if you're going to be 99% confident, then you're probably going to cast that net a little bit wider just to catch that and make sure. That's all I have for the T interval procedure. If you have any questions, just please let me know. I'd be happy to help, and I'll see you in the next one. Bye-bye.